Hello everyone. In this session we discuss about axiomatic systems. An axiomatic system is a foundational framework in mathematics and logic consisting of a set of axioms which are basic self-evident truths from which other truths are logically derived. So here axiomatic system is a formal framework for making a valid logical reasoning. So in previous sessions I told you about how logic help us in developing AI systems. We covered two methods of making a logical reasoning, truth table and natural deduction system, and third one is our axiomatic system. So axiomatic system is basically used in automatic theorem proving in AI systems. Automatic theorem proving means we are proving a new logic is generated from old logic, or we are saying that whether a new things can be derived from old premises. So we prove some theorem. This automatic theorem proving is applied in several ways in artificial intelligence systems. Like suppose we want to check correctness of a program, whether this algorithm is working correctly or not. It has to go through from starting to end. We have to prove that it is going in a right way. Suppose I want to check software behavior, means whether software is behaving as per expected behavior. I want to make a comparison of expected behavior and actual behavior. Then I have to make some assumption and prove that it will behave in a correct way. So what we do, we take help of this method of axiomatic system, which is which uses the basic axioms of our geometry. So axiom means is a basic self-evident truths. See, we are proving theorem, automatic theorem proving means we want to prove something. So if you want to prove something, we can't prove something from anything. So we can't prove something from nothing. Means to prove something, we require one basic building block from one basic truth, self-evident truth. Self-evident truth means we don't require proof for that truth. Like suppose I say sun rises in the east. So this is a truth, and you don't require a proof for this sentence that sun rises in the east. So such kind of axiom, we take one axiom and we try to derive new axioms in this system, so that we try to prove new theorems from existing axioms, means self-evident truths. We take one axiom as our fundamental input, fundamental use, and we take some undefined terms, and we prepare a model of those model that realizes these undefined terms, and we apply rules of inference. Like in my last session we covered several rules of deduction rules. We apply them logically and we try to prove the theorems. Let us see a small example. See, now we take axioms, self-evident truths one by one, and we apply the rules to prove our theorems. A small example, let us say I have three axioms in my system. There are three true things which don't require a proof. Like axiom 1 says that every computer set has at least 2 players. Axiom 2 says that every player has at least 2 computer set. Axiom 3 says that there exists at least 1 computer set. So these are three self-evident truths I have in my knowledge system. Now I want to prove one theorem, whether really a player exists. By looking at these three axioms, I have to tell whether really a player exists in the system. So how we infer this, we prove that whether a player exists in the system. So I take help of first axiom says that, by third axiom we can say that it is saying that a computer set exists. So that is indirectly giving me a clue that when a computer set exists. Second axiom is saying that it is giving a clue that the existing computer set must have at least 1 player. So this axiom, third axiom is saying that a computer set exists. It is from this I can from by taking this as a input, from using first axiom I can say that when a computer set exists, every computer at least 2 players, that means there is at least 1 player, so a player exists in the system. Means here a player exists in the system, that is what I proved from these axioms. So it is not like our earlier, like where truth, false and things applied. So means if your knowledge base has a sufficient number of axioms, a new axioms or new inferences can be made like this. This is, we can say it as a axiomatic system. Now suppose we take another one problem, where suppose I have a axiom. I take a first I have one axiom A1 as every ant has at least 2 paths, and axiom 2 says that every path has at least 2 ants, and axiom 3, there exists at least 1 ant. So these are 3 axioms I have given. From these 3 axioms I want to prove a theorem. Suppose I want to prove a theorem that so somebody asks, suppose prove there exists a path. So to prove that there exists a path, we take first we introduce A3 axiom. So when we introduce A3 axiom, it says that there exists at least 1 ant. So after looking at, we introduce when ant exists, every ant has at least 2 paths, that is second axiom is giving hint. So when we have a second axiom, so it is saying that at least 2 paths means there exists a path. So this is a simple way of proving things, but as the axioms grow, like this, inferring from these existing axioms, it will become a difficult. So what we do, we create one model that realizes all these axioms. If in that model, if everything is true, we can say there is a perfect axiomatic system for making new theorems. See, as my previous one, suppose first as per axiom 1, let us say 2, we make a B. I define it as A and B are ants, and connections are like a paths. So suppose there are only 2 ants in the system, I have this one. Suppose there are 3 ants in the system, so I make a model like this, where ABC represent ants and these edges represents path. Means whether all my 3 axioms are true or not for this model. So what first axiom says that every ant has 2 paths, it is true. Second axiom says that every path has at least 2 ants, this is also true. And the third axiom is there at least 1 ant. So now this model is satisfying 3 axioms, and this model is also. Suppose A, B, C, D, E. Here I have I can make so when 5 ants are there. Here what I am doing, I am creating a model for undefined terms. In my problem, ant is undefined, path is undefined, and has is undefined. Means here has is a relation, whereas these are some objects. These undefined terms for these undefined terms, I am creating a model with the help of axioms, so that if that model is true for all the axioms, I can infer a new theorems from that system. That means if I have some models may be true for some axioms, may be false for some other axioms. Some models may be true for all axioms. So I take one perfect model. I am creating a model, and I am trying to define these undefined terms in that model, and I try to prove new theorems. Like this, a axiomatic system has basic components. So, axiomatic system, whenever we try to prove something, first we require the axioms, where are fundamental assumptions of accepted proof. Then I take primitive terms in that one, like undefined, like in my problem I have ant, path and has are the primitive terms. They are next one. I created 3 rules, like every ant has 2 paths, every path has 2 ants, like this. From these 2 terms I proved one, like so. These are 4 components of a axiomatic system. Now when we are making like this axiomatic system and proving new theorems, we have to take care of 3 properties. First one, consistency. A system is consistent. Let us work. That is, first we say, first property of a axiomatic is independence of a axiom. Axiom is to be independent if it cannot be derived from other axioms in the system. So as I told you, axioms are basically self-evident truths. So that means one axiom cannot be derived from other axiom. Suppose I say sun rises in the east is a universal truth, that is an axiom. There is no other sentence that generates this sun rises in the east, which is true. That means it is an independent sentence, that is independent axiom. We can't prove it as a theorem, we can't take it as a theorem. They are included, but they are not treated as a for deriving as a theorems. So independent axioms are important. Means in AA, when we are representing a knowledge, if there is no independent axioms, there is a chance of redundance. Means we are taking axiom repeatedly. So it leads to inefficiency, conflicts and unnecessary complex while deriving the theorems automatically. Means redundancy of the axioms you can reduce if you include only independent axioms. So that is first property we should take care while taking axioms. Second one, consistency. A set of axioms is consistent if it is impossible to derive a contradiction from them. No axiom leads to a situation where both statements and its negation are derivable. So when we are making a group of axioms for our automatic theorem proving, we try to make that our system is consistent. Those axioms are consistent. Like suppose in a medical field, I created one AA systems that try to diagnose the diseases. For one set of axioms of that medical knowledge, it automatically proves that a disease exists by looking at some axioms in one case, and immediately in another case there is no chance of diseases. Means I am making arguments and its negations simultaneously, that leads to inconsistency in the AA system. So consistency of axioms is another important thing. First one, independence. Next, consistency, and third one, completeness of axiom. So the completeness of an axiom refers to ability to derive every statement that is semantically true within that framework. Suppose I have created a set of axioms in my system. So if based on those systems, every true statement can, if it can be derived from those systems, then I can say it has a completeness of the axiomatic system. Means when axiomatic system is complete, every true statement that belong to that knowledge base can be derived. So these are the 3 properties, like independence, consistency and completeness should be preserved while making a logical conclusions from the axiomatic systems. So, in next session we solve one problem using a axiomatic system. Thank you.